Let us look at HashMaps next, which enables instant lookup. Imagine you're building a contact directory app with 10,000 entries. A user types in John Smith and hits search. If you scan through the list one by one, you might check thousands of names before finding the right one. Slow, frustrating, and completely impractical at scale. But what if, instead of searching, you could compute exactly where John Smith lives in your data structure and jump directly to that location? No scanning, no waiting, just instant retrieval. That's the power of hashing. It transforms the problem of finding a needle in a haystack into a problem of knowing exactly which haystack to look in, and where in that haystack the needle sits. Hashing, know exactly where to look. In the next few minutes, you'll see how hash functions work, why they enable big O of 1 lookup time, how collisions are handled gracefully, and why every search engine, database, and cache system you use daily depends on this one elegant idea. So how does hashing actually work? It's beautifully simple. You take a key, like a contact name, and pass it through a hash function. The hash function is just a mathematical operation that converts the key into a number, and that number becomes the index in your array where the data is stored. Critically, the same key always produces the same index. That's what makes retrieval instant. You don't search for the data. You compute where it lives and go directly there. Let's watch this happen. We'll hash 4 different names and see how each one maps to a unique index in our contact array. Notice that the hash function doesn't care how long the name is or what letters it contains. It just outputs a valid index between 0 and the array size. This deterministic, direct mapping is the core mechanism that eliminates search time entirely. This consistency is fundamental. It means that whenever you need to retrieve John Smith's data, the hash function will always point you to the exact same location in the array, making data access incredibly efficient. And this is the power of hashing, a direct, computed link to your data. The hash function ensures that no matter the input, the output index will always be within the defined array boundaries, preventing errors and ensuring data integrity. Collisions happen. 2 different keys can produce the same index, and that's completely normal. The hash function is deterministic, but it's also compressing a huge input space into a limited number of array slots, so overlap is inevitable. Let's see this in action. The key insight is that collisions don't break the system. They're handled gracefully, using a technique called chaining. When 2 keys hash to the same index, instead of overwriting the first entry, we store both in a linked list at that slot. During lookup, we hash the key to find the index, then scan only the short chain at that slot, not the entire table. Because collisions are rare when the hash function is good and the table isn't too full, the chain is typically very short, and lookup remains fast. This profound efficiency gain arises because when using a hash table with chaining, we quickly pinpoint the correct slot and scan only a few entries. Compare this to a linear list where finding an item might require scanning 10,000 entries, leading to significantly slower operations. This is why hash tables are fundamental for high-performance data access. But efficiency isn't guaranteed indefinitely. As a hash table becomes more populated, its load factor increases. This means more slots are occupied, leading to more frequent collisions and longer chains. If chains become too long, lookup time degrades, moving away from that ideal constant time performance. To maintain optimal speed, the solution is to resize the hash table, creating a larger array when it gets too full. This state, with a high load factor of 70%, signals that the table is approaching its performance limit. Understanding when and how to resize is crucial for maintaining the efficiency benefits of hash tables in real-world applications. To prevent performance from degrading, we monitor something called the load factor, the ratio of entries to array size. As you keep adding entries, the hash table fills up. More entries mean more collisions, longer chains, and slower lookups. Let's watch a table fill up, hit the threshold, and resize itself to maintain performance. When the load factor crosses a threshold, typically around 75%, we resize the table. Resizing means creating a new, larger array and rehashing every entry into the new positions. Yes, resizing is expensive. It's an O of N operation. This process effectively reduces collisions and restores constant time lookups by spreading out the data. While the individual resize operation is computationally intensive, its cost is amortized over many subsequent, faster operations. This is called amortized constant time, meaning the average cost per insertion stays O of 1, because the O of N resize happens infrequently. Hashing isn't just a clever trick for contact directories, it's the invisible engine powering the systems you use every single day. Search engines like Google cache billions of queries using hash tables, answering repeat searches in microseconds instead of querying massive databases. Databases index records by ID or email using hashing, turning what would be full table scans into instant lookups. Password systems hash your password and store only the hash, so even if the database is compromised, your password stays safe. And deduplication systems. Whether you're uploading files to the cloud or processing terabytes of data, use hash tables to detect duplicates in constant time. Every one of these systems depends on the same core idea you just learned. Compute the location. Don't search for it. Hashing is fast, elegant, and foundational. If you want to master data structures that scale, understanding hash tables deeply is non-negotiable.